Welcome to an exploration of advanced quantum mechanics, where classical electromagnetic interactions between zitterbewegung-driven Dirac particles reveal surprising, foundational connections to the Schrödinger wave function. The paper models Dirac particles as rapidly circulating point charges, whose magnetic force modulation, dependent on phase differences and relative motion, mimics the behavior of de Broglie matter waves. Examining the Coulomb-like, inverse square magnetic forces, we discover that phase modulations vary with particle momentum and velocity, linking de Broglie wavelengths to relativistic kinetic energy change. In time-symmetric electromagnetic interactions, advanced and retarded fields combine to produce modulation factors that formally reproduce the Schrödinger equation structure, elegantly bridging classical theory with quantum behavior. Through rigorous mathematical derivations, the analysis demonstrates that replacing Planck's constant with intrinsic spin recovers a Schrödinger-like equation, thereby supporting a classical origin for quantum wave functions. In conclusion, classical Hamiltonian dynamics with time-symmetric electromagnetic forces yields a quantum wave phenomenon, a compelling, parsimonious explanation urging further investigation into the classical roots of quantum mechanics.
The paper we're diving into today is Quantum Wave Mechanics as the Magnetic Interaction of Dirac Part by David C. Lush. It's a mouthful, I know, but stick with us. This one's actually trying to answer one of the deepest questions in physics. How is quantum mechanics connected to classical physics, specifically through the magnetic interactions of spinning particles like electrons?
Yeah, so the central problem here is all about the quantum wave function, right? That mysterious thing in quantum mechanics that tells us where particles might be. Lush asks, could this wave function actually emerge from just classical, relativistic electromagnetic interactions between particles if you model them with internal circulatory motion, the so-called zitterbewegung or zitter model?
Right. So instead of the wave function being this mysterious, standalone thing, he's looking at whether you can get something that looks and acts like the Schrödinger wave function, pretty much the core object in quantum mechanics, just from considering electrons as tiny charges spinning really fast at nearly the speed of light.
It's worth pausing on why that's a big deal. If you could show that all that weird quantum behavior, like particles being in two places at once or quantum tunneling, if that just pops out of good old classical physics with a tweak, it would change the way we think about reality. It doesn't solve everything, but it maybe demystifies a lot of quantum theory.
Exactly. So what Lush does is he looks at the force between two of these zitter particles. Think of electrons as tiny spinning tops, but moving so fast they're practically at light speed. When you include the magnetic interaction between them and make things time-symmetric, meaning you include advanced and retarded electromagnetic interactions, a bit like Wheeler-Feynman's absorber theory, a new pattern emerges.
The core finding here is really cool. The magnetic force between these two spinning charges is modulated, meaning it oscillates, in a way that's mathematically very similar to the quantum mechanical wave function. It solves an equation that's almost the same as the Schrödinger equation, although in the standard relativity, it's almost because of a factor of 2 difference.
But here's where it gets twisty. Lush introduces a modified version of relativity from OSIAC, where the relationship between mass and energy is E equals mc squared over 2, not the usual mc squared. When you use that, the modulation matches the Schrödinger equation exactly, with no extra factors.
I mean, that's pretty wild. If this alternate relativity is correct, which is a big if, then quantum mechanics, or at least its central wave equation, might actually just be a feature of classical physics with this zitter model. And to be fair, that's far from universally accepted, but it's an interesting proposal.
And let's not forget, he brings in the Wheeler-Feynman absorber theory to help explain how particles can have time-symmetric interactions. It's a bit mind-bending. Advanced waves, retarded waves, the idea that absorbers in the future and past play a role in what happens now. Sometimes it almost sounds like science fiction, but it's tied to real equations.
Absolutely. The upshot is that, under this framework, the wave function isn't some mystical cloud, but a manifestation of synchronized, or sometimes desynchronized, internal motions of spinning particles, communicating with each other via classical electromagnetic forces. It recasts quantum probabilities in terms of these phase differences between spinning particles.
There's nuance, of course. For example, Lush points out this only seems to work perfectly for particles with aligned spins and equal mass, which doesn't always fit the messy reality of protons, electrons, and composite particles. He speculates about deeper structures, preons inside electrons and quarks, which, honestly, is a whole other rabbit hole.
Yeah, and he admits there are still open questions, like how this framework handles cases where spins aren't aligned or particles don't have equal mass. He suggests that some modifications, like those preon models or more complex absorber behavior, might fill the gaps. But it's very much work in progress.
In the end, the real takeaway is that quantum mechanics might not be as mysterious or as fundamentally other as we sometimes think. Academic research like this doesn't settle things, but it gives us fresh ways to connect ideas and see where classical and quantum blur.
Exactly. Whether or not Osiak's relativity is right, or if every electron is really a bundle of jittery charges, the beauty here is that science keeps digging deeper, asking, could we make sense of the universe with the tools we already have, if only we look at them differently?
The paper we're diving into today is called Spin-Spin Interaction as Quantum Phase Measurement and the Mechanism of Atom Formation by David Lush.
Yeah, that's quite a title. And honestly, I feel like just the first line sets the scene for this incredibly deep re-examination of some basics from both quantum mechanics and classical electrodynamics.
Exactly. I mean, Lush is really trying to poke at what is at the heart of atomic formation. He brings up this idea that maybe we haven't really appreciated just how strong magnetic or spin-spin interactions could be under certain circumstances. Especially if, as the Dirac theory suggests, the electron always moves at the speed of light in these internal zitterbewegung patterns.
Right, and let's maybe take a second on that. The zitterbewegung thing, if you're not familiar, that's this idea from quantum theory that electrons aren't just sitting still when you think of them as being stationary. Instead, they're doing this wild, jittery dance at enormous frequency. The Dirac equation predicts it, but usually we treat it as a mathematical quirk, not a real motion.
Yeah, and Lush is saying, what if that's not just a quirk, but it's something you can actually use to explain how atoms come together? He posits that these high-speed, circular charge motions, when you consider their intrinsic magnetic moments, could lead to spin-spin interactions that are strong enough to rival the standard electric, or Coulomb, force between charges.
That leads to the core question in the paper, right? Which is, could these spin-spin magnetic interactions actually be the real driver behind atomic formation, instead of the classic view where it's just electric attraction holding everything together?
And that question matters because, if it's true, then our entire fundamental picture of what holds atoms together would shift, from seeing the Coulomb force as everything to acknowledging that a hidden, really strong, spin-driven force is playing a bigger role.
One thing that caught me is how Lush argues that this interaction doesn't always appear. It actually depends on having particles with equal mass and spins that are aligned. So, like, two electrons with the same spin orientation could attract magnetically with a force similar in strength to the regular electric force, but if their spins are anti-aligned, this force averages out.
It's very selective, this coupling. And of course, that fits, in a weird way, with quantum statistics and why some atomic configurations are stable and some aren't. But Lush doesn't stop there. He speculates that quarks and leptons, so the really fundamental building blocks, might themselves be made from more fundamental spin half particles. Which, to be honest, is kinda wild, since it revives these ideas about substructure inside elementary particles.
I think that's what's kind of both exciting and daunting about this paper. It's not just proposing a tweak, It's basically saying, hey, you know the electron? What if that's not fundamental? What if it's made of three even tinier things with their own spins and internal dances?
Yeah, and even photons might have structure, as Lush brings in. That, by the way, is something de Broglie and others mused on decades ago, but never really became standard.
So, in terms of method, much of what Lush does is take the classical electrodynamics we know and push it into this high-speed, almost always at light speed regime, and then calculates what the electromagnetic fields would do if these zitter motions were real. He then compares these magnetic force modulations to the de Broglie matter wave, so the oscillation of these internal phases of the electron matches the famously mysterious wave function phase in quantum mechanics.
Precisely. And he argues that this quantum phase might not be some abstract mathematical thing, but actually a real physical phase between two zitter motions. So interaction between electrons becomes a measurement of their phase difference. That's a neat way to reinterpret, say, why quantum interference happens.
It's pretty wild. It reminds me a bit of, oh, this is such a tangent, but I remember hearing about how oil droplets on vibrating surfaces can sometimes mimic quantum interference effects.
Oh, right, those bouncing droplet experiments. Basically, a classical system somehow showing quantum-like results. That's a fun analogy, even if the scale and context are so different.
Anyway, coming back, Lush even suggests that this could help explain the so-called spin-orbit coupling anomaly in atomic physics. Normally, we say there's a weird factor of two discrepancy that's only fixed by some clever relativity tricks. But here, he says if photon energy is recalibrated, the problem might resolve itself much more naturally.
It's worth saying, though, Lush recognizes the big caveats. The paper we're diving into today is Spin-Spin Coupling as the Origin of Atomic Binding by David Lush. I gotta say, this one's a bit of a brain bender, but it really challenges the way we typically think about atoms holding together.
For sure. So, right off the bat, Lush is taking on this core question. What actually binds electrons to atomic nuclei? We usually think about the Coulomb force, that good old attraction between positive and negative charges, as the glue in atomic structure.
Exactly. But Lush digs into this alternative, almost radical idea. He's kind of poking at the holes in the standard story, especially when you look at things through the lens of quantum theory, de Broglie-Bohm specifically.
Yeah, he points out that in Bohm's version, for atomic states, this so-called quantum force actually cancels out the Coulomb force mathematically. That's pretty wild, right? If the very force we usually rely on cancels, something else has got to be doing the job of keeping atoms from flying apart.
That's the crux of it. The big claim is that magnetic interactions, specifically spin-spin coupling from charges moving at relativistic speeds, could be responsible for atomic binding. So, essentially, it's not just static charges pulling on each other, but their intrinsic spins. Think of them spinning, almost like little tops, creating magnetic forces that act kind of like the Coulomb force.
And Lush leans on this zitterbewegung concept. You ever heard that term before this? It's this jittery motion predicted by the Dirac equation, where instead of picturing an electron as sitting still, or even just orbiting the nucleus, it's kind of zipping in a crazy, almost light-speed little circle.
Right. And if you model electrons and similar particles as these zitter particles, you get these highly dynamic internal motions. The wild thing is, these motions generate their own magnetic fields, and the theory shows that, under certain conditions, the resulting magnetic force between two such particles can have the same form as the Coulomb attraction. So, a 1 over r squared radial force, just like what you see with electric charges, except it comes from these internal spins.
But there's a twist. The strength and sign of this magnetic force depends on the relative phases of the two particles' spins. In some cases, it can modulate, That is, it oscillates depending on how the two particles' internal jitters line up over space and time.
Yeah, and the really cool connection is that this modulation ties directly to the de Broglie wavelength, the wavelength associated with quantum matter waves. So Lush is making this bridge. He's saying the very quantum properties we normally interpret probabilistically could stem from concrete classical spin-spin effects.
The methods are pretty deep in the weeds, mathematically speaking. There's a lot about retarded and advanced electromagnetic potentials. Lush argues that if you treat the electromagnetic interaction as time-symmetric, considering not just signals propagating forward, but also backward in time, you end up with some very strange but potentially significant consequences.
There's a subtle point there. Advanced fields are not something we experience in daily life. You don't, receive a light signal before someone sends it. But at really tiny scales, in the math, these advanced effects could, in theory, cancel out the ordinary Coulomb force we always talk about.
Which could be why, in Bohm's quantum picture, the usual glue goes missing, and something else, a spin-based magnetic glue, has to take over. But hey, this brings up a digression. Doesn't this make you wonder if, the macroscopic symmetries we see, like time only going forward, are just a quirk of scale or statistics? Quantum mechanics is always hinting at a much weirder universe.
Yeah, sometimes I wish my coffee would arrive before I order it, but, causality has its limits. Back on track, though, there are some objections, and Lush is upfront about them. For one, this only works if particles have parallel spins, and only if their masses match. So, not a perfect explanation for every atom.
Plus, there's little observational evidence for these advanced fields, or for this zitterbewegung, being a physical reality. It's more of a theoretical playground, for now anyway.
True. But even so, the implications are interesting. If this mechanism plays any role at all, it suggests atomic structure might be more about deep, dynamic symmetries, spin, time reversal, and motion, than about static charges. It's a reminder that science isn't about finding one absolute truth, but about exploring new ways of seeing familiar things.
Exactly.